Suppose we have two groups, G and H, and homomorphism between these two groups, F. Then we can define the kernel of this mapping, this homomorphism, F. So that is all the elements of G that that are mapped to the identity element of H. Okay, so this is called the kernel of F. And this is a normal subgroup of G. Now, conversely, if we have a group G and its normal subgroup, say N, then we can define some group and homomorphism between these G and let's call this H, and such that the kernel of this homomorphism is this given subgroup N. Let's see how we can do this. Let's recap again. So here we had two groups, G and H, and homomorphism between these two, and then we found the kernel of F, which was a normal subgroup of G, right? But next we first have a group G and its normal subgroup. Its normal subgroup. And from these two, we define some group H and homomorphism such that the kernel of F becomes this normal subgroup. Okay, so given what are given are G and N, and what's derived are H and F. So that is kind of opposite from the previous scenario, where the given were G, H, and homomorphism, and derived was the kernel of F, which was a normal subgroup of G. Now, first we prove a lemma. Suppose G and H are groups, and F is a homomorphism from G to H. And we assume that the kernel of F is K. Okay. Then let A and B be any elements of G. Then we have F of A is equal to F of B if and only if the cosets of K are the same. Okay, Ka and Kb are the same. In case you forgot the definition of the coset, Ka is the right coset of K determined by A. That is the set of all elements of this form. So K times A, where K is an element of uppercase K, the subgroup K. So let's prove this. Since this is if and only if statement, we have to prove both directions. Okay, so first let's prove only if part. So suppose f of A is equal to f of B. Okay, then let's calculate this A, B inverse. Then since f is a homomorphism, that is, this is equal to f of A times f of B inverse. But as we have seen before, this is equal to f of A and f of B inverse. But since f of A is equal to f of B, this this f of a is same as f of b and f of b inverse, so this is equal to the identity element of H. So this means a b inverse is an element of the kernel of F because it's mapped to the identity element of H. So by a previous theorem, this is equivalent to this Ka equal to Kb. So the only if part is done. Then next prove the if part. So suppose Ka is equal to Kb. Okay, then this means there exists some element K in the kernel K such that A is equal to Kb. So this means f of A is equal to f of Kb, but f is a homomorphism, so this is equal to f of k times f of b. But since k belongs to the kernel of f, then f of k is equal to the identity element of H. Therefore, this is equal to f of b. Therefore, f of A is equal to f of b. So we are done. Next, consider the following theorem. Suppose H is a normal subgroup of G. Of course, G is a group. And let G by H be the set of all cosets of G. Sorry, not G, H. So that means the elements of G by H is something like this. H, A, where A is an element of G. Okay. Of course, some of them are equal and some of them are disjoint with others, so there may not be as many elements as G in this set. Then let's define the binary operator within this set by the following. So HA times HB. So these are elements of G by H, of course. So we define this binary operation by this HAB. So AB is an element of G. So this is another coset, which is therefore an element of G by H. Right? Then this is this operation is well defined. And with this operation, G by H is a group. Okay, and we can define a mapping from G to G by H by mapping an element of G to the coset of H by A. Okay, so A is an element of G and HA is an element of G by H. Okay, so this defines a mapping. And let's call this mapping F. Okay, so then the kernel of this mapping F is actually H itself. So in this way, given a group and its normal subgroup, we can define another group G by H and the mapping with the kernel being the given normal subgroup, as we have motivated at the beginning of this lecture. Well, before proving this theorem, we need to understand what this well-defined means. Okay, we are saying this definition of binary operation is well-defined, but what does it mean? In the present case, this coset can be expressed in a different way. So A and A prime may be different elements, but their cosets may be equal. Okay, and similarly, we may have HB equal to HB prime, where B and B prime are different. So in this case, do we have the following equation? So HA times HB, is it equal to HA prime times HB prime? If this does not hold, then this means this binary operation depends on the choice of the representative element. So it may give a different result depending on the choice of the representatives. So in that case, this operation is not well defined. But this theorem says that is not the case. Indeed, we do have this equality. So the result of the binary operation does not depend on the choice of the representative elements of each coset. Okay, now let's prove this theorem. And first thing we need to show is that this operation is well defined. So that means we need to show that if HA is equal to HA prime and HB is equal to HB prime, then HAB is equal to HA prime B prime, right? So this part is equal to this, and this part is equal to this. So if they are equal, then the operation is well defined. Okay. So to prove this, so suppose this. Okay, so let's suppose this. Then this means there exists some elements, let's say H1, H2 in H, such that A prime is equal to H1A and B prime is equal to H2B. Okay, that's what this means. So A prime B prime is equal to, let's see, H1A times H2B, and H1A H2 is A inverse. So we add multiply A and multiply A inverse. So this doesn't change anything because it's the identity element. So this is equal to, just to make it easier to see, this has this form. So H1 times A times H2 times H inverse times A B. Okay, but this can be written in this way. So H times AB, where H is equal to H1 times A times H2 A inverse, which is an element of H. Why? Because H is a normal subgroup is normal. So this means A and H2 is of course an element of H, this normal subgroup. So A times A H2 times A inverse is an element of H. I mean, this is the this comes from the definition of a normal subgroup, right? And normal subgroup is a subgroup, so and H1 is of course an element of H, and this is an element of H, so their product is still an element of H. Therefore, A prime times B prime is expressed as A H times A B, where H is an element of capital H. Therefore, that means H A prime B prime is equal to H A B. Therefore, the product is well defined. Next, we show that the set of cosets G by H is a group. So we need to show that this G by H satisfies all the axioms of the group. First of all, this is closed under multiplication. By definition. Okay, because if you look at the definition, then by this definition, this right hand side is an element of G by H, so it is closed. And the next thing we need to show is that this multiplication is associative. Okay, so let's say let A, B, C be elements of G. Then H, A, H, B, H, C is equal to, so first we calculate this product, HC, and this is, so this times this, which is equal to H, A, B, C. Okay, but this is equal to, since G is a group, then this product between its elements is associative. So A, B, C, but this is equal to HA times HBC, which is equal to HA times HB times HC. Therefore, it's associative. The multiplication is associative. Then we need to show the existence of the identity element, but we show that H, which is actually equal to H times E, is the identity element. Of G by H. To show this, in fact, H E times H A, of course, A is any element of G, and E is the identity element of G. We have H E A, which is H A. And so multiplication by HE or just H does not change the other element. So it leaves the other element intact. So this is indeed the identity element. And the next thing is to show is the existence of the inverse element for each element. We show HA inverse is actually HA inverse. Okay. In fact, HA inverse times HA is by definition of multiplication. This is this, but this is E, which is the identity element. Therefore, this is the inverse of HA. Okay. Therefore, G by H is a group. Next, we define a mapping G to G by H, which is defined by f of A is equal to HA. This is a surjection. Is a surjection. This is obvious because every coset has a corresponding element A in G, right? So every element in G by H is the entire set of cosets is covered by this mapping. Therefore, it is a surjection. And this is indeed a homomorphism because if we apply a f of AB, then by the definition of this mapping, this is HAB, but by the definition of the multiplication, this is HA times HB, but this is f of A times f of B. Therefore, it's a homomorphism. And it's a surjective homomorphism. And finally, we need to show that the kernel of this mapping is H itself. So the kernel of F is defined as the elements of G such that f of x is equal to H. Well, this is HE actually, but just use the simplified notation here. Okay, so this is the definition of the kernel. And so what is this? So that is G and f of x is hx, but this should be equal to H. But what this means is that all elements of x is so such an element x belongs to H, right? Because of this equation. So this subset is H itself. Therefore, the kernel of this mapping F is the normal subgroup H itself. And we are done. Now let's note this. If H has a finite index, okay, so this is basically the number of cosets of H in G, then this is actually equal to the order of G by H. Okay, so the number of elements, so the number of cosets is the number of elements in this, because this is defined as the set of cosets. And of course, the index of H in G is infinite, then this group G by H is also infinite group. So in general, if we have a group and its normal subgroup H, and then we can define another group G by H, and this group is called a factor group. Or some people prefer to call it quotient group. Of G by H. Okay, so this is like a division of groups. So dividing G by H in a sense. Now let's define a few new terms, definitions. Okay, let G and H be groups and F be a homomorphism. Okay, then if F is also surjective, not only a homomorphism, but it is also a surjection. Then we say F is an epimorphism. Morphism. Okay, epimorphism or simply epi. Okay, and if F is injective, then we say F is a monomorphism. Or simply mono. Okay, and when it is an epimorphism, we write F from G to H, and we add another head here. So this is epi. And in the case of monomorphism, we write like F, H, and another. So we add this angular sign at the tail of this arrow. Okay, and if F is bijective, so that means it's both surjective and injective, then we say F is an isomorphism. Okay, or sometimes we call it iso. And we write like F from G to H and another angular signs here and here. So this signifies epimorphism, this signifies monomorphism. Together it signifies isomorphism. And if there exists an isomorphism between G and H, then if this is the case, then we write G and H are isomorphic to each other. Isomorphic, yes. Okay, basically this means G and H have essentially the same structure. That's what isomorphic means. Let's see an example. Here is the Klein for group, which consists of 4 elements with this Cayley table. And this group is isomorphic to the following group, let's say H, which consists of 4 2x2 matrices, 1, 0, 0, 1. And we've seen this example before, but let's repeat this here. And 0, minus 1, 1, 0, and 0, 1, minus 1, 0. So if we define a homomorphism or mapping, so E corresponds to 1, 0, 0, 1, and A corresponds to 0, 1, negative 1, 0, 0, negative 1, and B corresponds to 0, negative 1, 1, 0, and C corresponds to 0, 1, negative 1, 0. So this mapping, so let's define this mapping as F. This is a homomorphism, and in fact this is an isomorphism. You should verify this. Then this Klein group and H uh, as a group of matrices with matrix multiplication as the binary operation, they are isomorphic to each other. Next, consider our favorite example, the dihedral group of order 8, defined by this Cayley table. And we have seen before that the center of this group, ZD4, is this, E and B. And we know that the center is a normal subgroup. Okay, so let's find the quotient group, this. So this is something we have written like G by H before. In this case, G corresponds to D4 and H corresponds to Z of D4. Okay. Then let's see. So the identity element of this quotient group is ZD4 itself. Okay, and one element is Z4 times A, which is found to be A and C. And another element, Z4, so B, A, C are there, so it should be, let's say, D. And that will be D and G. And let's see, C. So the remaining element would be F, for example. And that will be F and H. So the elements of this quotient or factor group are E, A, B, C, each of which is a set, these sets. And from the theorem, we know that this set is actually a group by a proper binary operation. For example, A squared is defined by, so A is actually this element, so ZD4A times ZD4A. By definition, this is equal to ZD4A squared. And according to this table, A squared is B. So that is ZD4B. But this is equal to this. So this is equal to E. This is equal to E. So in this way, we can make a Cayley table for this group. And if you okay, let's see another example. AB, that is ZD4 A and B is D. A times D is F, and this would be equal to C. So F is here, so C. So in this way, we can construct a Cayley table for this. A, B, C, E, A, B, C. And if we continue this, we find, so this was E, and AB was C, and if you continue this, you find this result. E, A, B, A, E. And this is actually the same Cayley table as the Klein foregroup. Okay, so let's compare this with the previous example of this. So A times A is E, A times B is C, A times C is B. A times A is E, A times B is C, A times C is B. Okay, and for this row, B, C, E, A, B, C, E, A, and for this row, C, B, A, E, C, B, A, E. So it's a Klein foregroup. So the quotient group of the dihedral group of order 8 by its center is isomorphic to the Klein foregroup.